Ivan, can you hear me okay? Ivan, can you hear me okay? Okay, not sure if I'm speaking into the void or if you're responding. I can hear you guys, so I'm gonna assume that you can hear me. I'm gonna start talking and assume that if you cannot hear me, that someone will let me know. We'll just go with that. So hello, good morning. I hope that you guys are having a good second half of your week. So we had the chapter 4 quiz on Tuesday, and now we are just wrapping up with chapter 5. I do want to talk for a quick minute about the final, just because I've had a couple quick questions. So for the final exam, it is optional, which means you don't have to take it if you don't want to. If you do decide to take it, then your final exam grade will replace your lowest chapter quiz grade. So you're going to want to look at your chapter quiz grades and see if that is something that you would like to replace in some way. You will have your final grade without the final prior to making that decision. So we hope to process all of those on that Saturday, and then the optional final is the next week. But it is scheduled to be during the 2-hour time block that's listed on Spire, but it is a 1-hour final. So you'll have to use some of the time in that 2-hour time block. So just to give you that context, it is on Moodle, so you will take it on Moodle. So in your planning and preparing for finals, you can just keep all of that information in mind. I will send a more detailed information email about that later next week once we're closer to the end of the term and we have more grades in about how you can make that decision about whether or not you want to take the optional final. So today we're talking about some more stuff in chapter 5 where we're looking at area under the curve. So I'm going to go ahead and switch over to the dot cam. And so today we're going to do 5.2 and we will start 5.3 because that's a really long section, but we won't go all the way through 5.3. So I'll write that a little bit bigger. There was a typo that we'll get to in a minute. So last class we were talking about finding the area under the curve by approximating with rectangles, right? We did left-hand approximations, we did right-hand approximations, And as we were working through that, we said, okay, if we can put in more rectangles, right? If we can make delta t smaller and n bigger, we get a better approximation, right? We saw that when we did the example with the bike. We went from delta t is 2 to delta t is 1. And through that, we were able to see that we get a better approximation. And so by putting in more and more rectangles, what's going to happen is that eventually the overestimate's going to come down and the underestimate's going to come up, and then they're going to be the same, right? So if our left hand and our right hand approximation are the same, that means that we have found the exact area under the curve. So that's what we're talking about today. How do we get to the exact area under the curve, and what does that look like? So when we are talking about the exact area under the curve, we are going to use what's called an integral to represent that. And so there's different types of integrals that represent different things. So the integral that we're talking about is called the definite integral. Okay, and it looks like this. Integral from a to b, f of t, dt. So what does this mean? What does it tell us? How do we use it? All that sort of stuff. So first, a and b are the same as when we were doing the approximations. These are the endpoints. Okay, you can only get the area under the curve of a function if you have a defined starting and ending place. So these are where you're looking. F of t is the function that we are looking under to get the area under the curve. This is our function. So this represents the derivative of some function, and we're getting the area under that curve to talk about the original function. Now, this symbol here, which is called an integrand, and this symbol here, the dt, these are operators, which means that once we have calculated the area under the curve, they disappear. So think about, like, I don't know, when you do 3 plus 4 equals 7, right? The plus is an operator. It's something that tells you what to do. And once you do it, you don't have it anymore, right? So you don't say, like, where did the plus go? The plus tells you what to do. So the integral and the dt, they tell you what to do. They say, find the area under this function, and this is with respect to t. Now, why is it t? Because this says f of t. If your function had an x in it, this would be a dx. If it had a q in it, this would be dq. So this is telling you what the variable is. It will always match the variable in the function. Why do we need that? Because if you go on to take higher level math, if you take Math 128, or you go on beyond that, then you can take and find areas of things that are more complicated, where you have multivariable functions that have many operators that have more than one variable. We are only using one variable in this class, but it's still an important part of the operator. Okay, what does that mean? How does it work? What do we do with it, right? So this is an example that we sort of outlined at the end of last class. We didn't get to it, but I told you to sort of finish it up at home. So hopefully you had a chance to, but now we're going to do it sort of more exactly. So if t is in hours of a 20-hour period, the rate at which bacteria population is growing is given by f of t equals 3 plus 0.1 t squared. Okay, so this is a rate at which it's growing, and we want to find the total change in bacteria over this period, right? So we want to know, what is the area under this curve from 0 to 20? So we approximated it last class, but now that we know how to find it exactly, we're going to work on plugging this into our calculator to figure out the exact area under the curve. Okay, so I am going to pull this up on my calculator and sort of show you the syntax of how I'm going to enter this to get this number, to get the exact area under the curve. If you have a calculator similar to mine, if you have a TI, then most of the steps will be the same. If you have something like a Casio or a different type, you may need to Google integral and then the type of calculator you have, but I'm going to talk about the different TI syntaxes here. So you're going to start by pushing the math button. And then if you scroll down to number 9, you can also just hit 9. But if you scroll down to number 9, it says FNINT. That means function integrate. So you're going to hit enter. And when you do, there's two possibilities. So you may get something that looks like this. So this has the same structure as the integral. But if you have like a TI, I think 83, which is the other kind of calculator I have, you may see this on your calculator. So I'm going to first talk about how to enter it this way, and then I'll talk about the syntax for entering it this way. So when we want to plug this in to find the exact area under the curve, we're going to start by plugging in our lower bound, which is 0. And then we go up here, we have our upper bound, which is 20. And then over here, we have to enter our function, right? So our function is this 3 plus 0.1 t squared. So we have 3 plus 0.1. Now we don't have, ooh, my plus turned into a divide. Sorry about that. Plus 0.1, where was I? So now we need to put in the t squared, but the calculator uses an x. So you could change everything to t's, but you really just need a variable. So I'm going to use the x variable. So I have x squared. I just turned everything into x for the calculator because it's going to give you the same result, whether you're putting a t or an x there. It's just a variable placeholder. Then you're going to come over, and in the second part, you're going to put an x again. So again, that's just telling the calculator what the variable is. So once you have your function entered with the right bounds, you hit enter. You see we get 326.666. So I've rounded to 327. But that's what the syntax looks like to get that area under the curve. If when you do math 9, you get something that looks like this, the syntax for that is that you are first going to enter the function. So 3 plus 0.1 x squared, and then a comma. The comma is right here above the 7, if you can see that, right on the calculator above the 7. Then you're going to put an x because you're telling it what the variable is, and then a comma, and then the lower bound, comma, upper bound. So it looks like this. And then when you hit enter, you should get the same thing, that 326.666. So if you're asked to round, you just round to whatever the nearest number is. If you're not asked to round, then you enter it as you see it. So when we do this on a calculator, it is computing the exact area under the curve by fitting in a ton of these tiny little rectangles in the background. It's doing those calculations we were doing last time, but on a much bigger magnitude. Okay, so let's practice one here. I want you to use your calculator to compute the area under the curve of x squared plus 3x plus 1 between 0 and 3. So I also want you to take a minute to just write what the integral is going to look like with the bounds and the integral so you can get comfortable writing integrals, then plug it into your calculator and see what it looks like. Okay, I'm going to give you a minute and a half, see if you can get that plugged in, and then we'll look at it together. Okay, about 30 more seconds. Okay, so when we set up our integral, if we're just going to write it, we need to take the bounds, and the lower bound always goes on the bottom, and the upper bound always goes on the top. So this says find the area between 0 and 3 underneath the function x squared plus 3x plus 1 And then because we're using x's, we have dx. So that's what it looks like when we set up our integral. As a reminder, what we're finding is the area under the curve. So I put together a little graph here. This is the function x squared plus 3x plus 1. We're finding the area between 0 and 3. So you can see that it's curved. It's not like a nice geometric shape, but what's happening in the background of your calculator is that it's inserting a ton of these little rectangles to get that exact area. And then when you plug in the values using the method we talked about here, you get an exact area of 25.5. So the area under the curve is 25.5. And again, what that tells us is that the original function changes, it grows by 25.5 between 0 and 3. Okay. Now, we have to take a step back for a minute because although we've set up definite integrals to tell us the exact area under the curve, there's sort of an overlap between approximating area under the curve and finding the exact area under the curve that comes up in the way questions are asked. So I want to show you two quick examples of how sometimes when we ask questions that have integrals, we're not actually plugging things in or finding exact area under the curve. And so I want to make sure we practice this so that we can sort of learn to distinguish when we're plugging things in and when we're approximating with left, right, and best estimates. So the example here says for the function f of t in the table below, approximate the area under the curve from 10 to 20 f of t dt. So first I want to point out that it literally says we're estimating, right? So that's sort of like a flag for us that maybe we're not plugging anything in. Second, I want to point out that we don't actually have a function here, right? So there's no like x squared plus 3 or anything given that we could plug in. So here we have a table and we're asked to estimate. So why do we have an integral, right? Well, we have an integral because the integral is what we are approximating the area under the curve from 10 to 20. It gives us important information about the bounds. So what does that mean for us here? That means we are interested in what's happening from 10 to 20. So we're not as worried about the other stuff. We're going to do what we were doing before. We're going to figure out what's our A, what's our B, what's our delta T, what's our N, and then we're going to use that to do a left-hand estimate, a right-hand estimate, and then from there, a best estimate. Okay, so this is directly tied back to what we were doing last class. So I'm going to give you 2 minutes. I want you to try this out. See if you can figure out from the information given what these are, and then use that to compute the left and right-hand estimate between 10 and 20. Okay, so take 2 minutes, and then we'll go through it together. Okay, take about 30 more seconds. Okay. So remember that our A is our starting point. So here that's 10. B is our ending point. So here that's 20. Delta T is what we're counting by. So here we see that we go 10, 15, 20, and that our delta T is 5. And N is the number of rectangles we're using to approximate, which we can get by doing B minus A divided by delta T. So if we subtract those, we get 10. 10 divided by 5, that's going to give us 2. Okay. We could also get that by seeing that we have two sort of spreads here that we're approximating. So as a reminder, when we do our left-hand estimate, we're looking at how far apart our independent values are. So that's 5. That's the width of our rectangle. And then we're going to multiply that by the derivative value on the left. So of the two values here from 10 to 15, we pick the one on the left, which is 42. And then from 15 to 20, that's another 5. We pick the derivative value on the left, which is 51. Now we're going to multiply these things together and then add the two values up, and we're going to get 465. Okay. We also want to do the right-hand estimate, which is going to be the same thing, but instead we're going to pick the derivative values on the right each time. So from 10 to 15, again, that's a spread of 5. We pick the derivative value on the right, which is 51. And then from 15 to 20, that's 5. We pick the derivative value on the right, which is 60. We multiply and then add the two multiplied values together, and we get 555. And then finally, last but not least, we want to find the best estimate here by averaging these two numbers together, and that's going to give us 510. So again, the context of this problem is that we see a definite integral, but we're still using that to approximate because we don't have something we can plug in to make it an exact area under the curve. When we have data on a table, the best we can do is just use that data. We aren't able to get the exact area. We're just going to get our best estimate. Okay. A second example of this is with a graph. So here, notice that we have a graph of f of t. We want to use n equals 1 to determine bounds for the integral from 1 to 3 f of t dt. What does that mean, determine bounds? That means we're looking for an overestimate and an underestimate for the exact area under the curve. So again, the numbers on the integral are important to figure this out. We're using n equals 1, which talks about the number of rectangles we use. So we're trying to find an over and under estimate using a left and a right hand estimate. Okay, so I'm going to give you 2 minutes to see if you can sort of tie back what we were doing last time to this work. Hopefully you can figure that out, but take 2 minutes, see what you can do, and then we will go through it together. Okay, take about 30 more seconds. Okay. So again, the integral is going to give us important information about the bounds. We're interested in looking at the exact area between 1 and 3. So we're going to label 1 and 3 on our graph so we know where we're looking. N equals 1 means we're just using one rectangle to figure out our approximations. So let's start with a left-hand estimate. So when we look at 1 and 3, 1 is the left-hand marker. So we come up till we hit the function, then we come over at a constant rate until 3 to set up our rectangle. So here we see that this is going to be an overestimate because it's above the exact area, and the area has 2 in the width and 2 in the height. So 2 times 2 is 4, and that is an overestimate. When we do our right-hand estimate, and we have 1 and 3, we pick the value on the right to go up until we hit the function. We draw a constant line here. And we see that this is going to be an underestimate because we don't get all the area, right? It's going to be less than. So it's got a width of 2 and a height of approximately 1. So it's going to be 2, and that is an underestimate, which means that those are going to be the bounds of where the exact area under the curve needs to be. It needs to be between 2 and 4, right? So we can see that this is the over and that the red is the under, and that helps us sort of visualize what's happening. Again, n equals 1 means we were only using one rectangle. If we were to use n equals 2 or n equals 4, we would get a better estimate that would shrink the interval for the bounds. Okay, so again, if you see a definite integral in a problem, you still need to carefully read the instructions to see if you're plugging something into your calculator or if you're using the information from the definite integral to still do an approximation, because there's sort of two different approaches here. Okay, so let's keep going with some of our definite integrals where we're getting exact area under the curve. We want to get really comfortable plugging things into the calculator to get these areas. So for the next example, there's just some functions that sometimes are tricky to plug in. We have the integral from 1 to 3 sine x dx, the integral from 1 to 3 of e to the x plus 3 dx, and then the integral from 2 to 4 of ln x dx. So I want you to take 2 minutes and just make sure you can plug these into your calculator, that you can find these functions, that you can plug them in, that you're getting comfortable finding integrals. And so you're just getting the value out for each one. So try that out, take 2 minutes, and then we'll just quickly go through what the areas are to make sure they're matching what you're getting. Okay. Okay, take about 30 more seconds. All right, so there's not really much work to show on these. I'm just going to tell you the values that I'm getting on my calculator. If you are having trouble getting the same values on your calculator, if you're getting like syntax errors or things aren't going through correctly, definitely stop by Drop In Help. We're happy to go through the calculator with you. to figure out, what's going on. Sometimes there's just like a weird setting, but we can try to troubleshoot it. Or you, like I said, you can Google the type of calculator you have plus definite integral, and you should be able to find like a YouTube video if that's your preference. But these are the values you should be getting when you plug in these different functions. If you're not getting those, you should go back and look at your parentheses or things like that to make sure that you set things up correctly. Okay, so in general, the reason why we want to use definite integrals is in practice, like in sciences or in business, we often know something about the rate at which something is changing. And we want to use that to talk about the original function in some meaningful way. So the next couple of examples we're going to look at both setting up integrals, but how to use the information from the integral to answer the question at hand. So example 5. It's important for pharmaceutical companies to test the characteristics of drugs they design. Obviously, the strength of the drug is given by R of M, where M measures the dosage and the amount of medicine absorbed in the blood. Suppose an experimental drug changes a patient's temperature at a rate of R of M equals 3M squared over M cubed plus 1. I'm going to write that a little bit bigger because you're going to have to use that in a minute. Okay, so this is the rate at which the temperature is changing in degrees per milligram of the drug. So that means if you change the number of milligrams, that's going to change the rate at which the temperature is rising. So we want to find the total change in temperature resulting from the first 4 milligrams of the drug. So if we were to give somebody 4 milligrams of the drug, what is going to be their change in temperature? Okay, so what we need to do here is we need to think about how do we set up our integral? What are the bounds going to be? And then how do we plug it in? So this is sort of like a 2-step problem here. So first I want you to set up the integral and write it with the correct variables as given in the problem, right? Just to practice that and making sure we can set things up. And then I want you to plug into your calculator to calculate how much the temperature actually changes. Okay, so take 2 minutes, see if you can set that up and then calculate it out. And then we'll go through it together. Okay, take about 30 more seconds. All right, so if we're going to set up this integral, we're going to set it up with the bounds of 0 to 4 because we're looking at the first 4 milligrams, which means that we went from 0 to 4, and we want to see the impact of that change over those 4 milligrams. And then the function, if we were setting this up as an integral, it's going to look like this. Whenever you set this up as an integral, you want to use the variables that are given to you within the problem to be consistent with what's happening. However, when we plug this in, you can change these to x's for your calculator to make things a little bit easier on the computing side. And when we plug it all in, we get 4.17. And this is going to be degrees because remember, when you integrate the function, it's telling you how much the original function changes. And so that's telling us about how the temperature changes of this particular patient. So we get 4.17 degrees. Okay, So we can kind of see why having a way to take a rate of change and turn it into information about the original function might be helpful. The more sort of useful way this comes up is for predictions. So one of the most powerful aspects of calculus is being able to predict things through the different methods that we're learning about how these things are related. So this is an example of this. So the greenhouse effect is the rise in temperature that the Earth experiences because certain gases prevent heat from escaping the atmosphere. So this all has to do with climate change. You may have heard about this before, about the greenhouse gases and the greenhouse effect. According to one study, the temperature is rising at a rate of 0.014 T to the 0.4 degrees Fahrenheit per year, where T is the number of years since 2000. So this particular model was a model that did come out in the year 2000. The reference is here. It's in the notes if you want to look it up. I think this model is slightly outdated now. I think it's changed because of the impacts of humans over the past 21 years, but this was a fairly accurate model of how temperature was changing in the year 2000 when this model was derived. So T is the number of years since 2000. Given that the average surface temperature of the Earth was 57.8 degrees Fahrenheit in the year 2000, so this was the average temperature, we want to predict the average temperature in 2200, 2300, and 2400, right? So these are obviously many years from now, and we won't be here to see that, but we want to know how that temperature is changing. So this is a rate. And what we need to do for each of these is figure out what is our upper T value, right? Since we're measuring in years since 2000, this first one will be T equals 200, so over 200 years, and you can sort of extrapolate from there. But for each of these three scenarios, we want to set up an integral to integrate the rate to see how much the temperature will change. And then we need to figure out how to incorporate that with the average temperature from before. So I'm going to give you about 3 minutes to see if you can put this all together, if you can set up these models, these three prediction models, to figure out what the average surface temperature will be in each of these years by integrating our rate of change here. Okay, so take 3 minutes and then we'll go through it together. Okay, take about 30 more seconds. Okay. So for each of these, the rate is going to be the same for all of them, right? We're all based on this rate of what's happening in the year 2000. We were able to tell how quickly the temperature was rising by looking at data from 1990 to 2000 and coming up with an accurate model of how it was changing at that time. So the function is the same for all of these. What's different for each one is the upper bound for how long we are at this rate, right? So when we plug each of these into the calculator, we expect that these numbers are going to go up, right? Because we've been at this rate for a longer amount of time for each one. So for the first one, when we plug it in, we're going to get 16.65. For the second one, we get 29.37. And for the third one, we get 43.94. But we have to remember that this is how much the temperature changes. This is the change in temperature. And so for each of these, we need to add this to the initial amount, which was 57.8, which was the temperature in the year 2000. And then by adding those together, we are able to get our prediction value. So what do we predict that the average temperature will be in these years? Well, this one will be 74.45 degrees. This one will be 87.17 degrees. And this one will be 101.74 degrees. Okay. And so we can see that the average temperature of the Earth is going up, right, because of this greenhouse effect. Now, there are more up-to-date models now that you can find online, and you can use those to do predictions in the same way. If you can find the rate at which the temperature is changing, and you can find the current average surface temperature, you can find a more up-to-date model. And my understanding is that more current models are a little more drastic, where the temperature is rising faster than it was in the year 2000. So if you are someone who is thinking that you might be a scientist who works on climate change or things that have to do with these types of effects, it's worth looking up the newer models and seeing how you might be able to use them to make some predictions of what's going on in our current world, right? So that's sort of another example of where we would use this idea of rates of change to help us understand what might be happening at a later point in time, okay? So the next thing we're going to talk about is sort of the beginning of 5.3, which overlaps with the end of 5.2. So they are definitely related. I'll cover up this one. So what we're going to talk about now is some assumptions that we've been making for all the work we've done so far that haven't been really explicit yet, right? So we've been talking a lot about area, right? Area under the curve, area in, helping us find things. So some of the areas we've talked about, right? We did a rectangle, which is base times height. We did a triangle, which is 1/2 base times height. We talked about the integral, which is going to help us find, right, this area that maybe isn't a rectangle or a triangle. We can use the definite integral to get this area here, right? So we've been talking about area a lot. And what I want to say is that when you talk about area in high school, in geometry classes or things like that, we talk about area as how much space a particular shape takes up, right? So when we do this calculation, we're talking about how much space it takes up on a coordinate plane, right? And so when you talk about area previously, it's always positive, right? It doesn't make sense to have negative area. You wouldn't say this triangle has an area of -5, right? That doesn't make sense in the context of that particular definition, but we are going to expand our definition within this calculus class, but we're going to start by talking about what positive area means in calculus, which is not quite the same thing, right? So we're not necessarily talking about how much area in space something takes up. We're talking about the area between a function and the x-axis, right? We're talking about this particular shape. So all the functions that we've looked at so far have been positive, which means they're above the x-axis. And that is by design, because we weren't ready to have a conversation about if it wasn't above the x-axis until we really understood this idea of fitting in rectangles to approximate area. So we talk about that f of x is continuous and positive. So all the functions we've looked at have been continuous and above the x-axis. And we've been approximating by drawing in these little rectangles, right? So these just represent the generic rectangles where the width is delta x and the height is the y value you get from plugging in that x value. And those are little areas of rectangles, right? So let's consider x squared for a minute, right? So x squared is a parabola. Goes on forever. If we were going to talk about the area under the x squared curve, we would approximate rectangles. Let's say we have them that look like this, maybe, depending on what our delta t is, but we know that we're fitting in a lot of little rectangles here, right? So for each one, the width is delta x, right? That's how wide each rectangle is. And then we're multiplying it by the height, right? So we're doing base times height to get these areas. And when we do that, the y value is positive. So this is consistent with what we learned about area in other classes, where the area is width times height, the y value is positive. So we end up with a positive area. And we know from before that if your function is positive, that means that the original function is increasing, right? That was a property that we had before. And so since we've only been looking at functions that are positive, which means above the x-axis, all of our answers were that the function was increasing. And so we have a lot of examples of why we'd want to do that. So we're going to just do one more example. This one is a little nuanced with the units, but we see that there's a important place for functions that are positive and increasing, right? There's a ton of them that we want to model. So here, this example, the rate at which your income is changing is given by I of t equals 1.85 to the t in dollars per month, where time is in months. Find your change in income during your first year working. So this is an example where this is a completely positive function. I want you to take, I don't know, 1.5 minutes to set up the integral to find out how much your income is going to change, the total change, by integrating this rate. Be a little bit careful with the units, read it again, see if you can set it up and calculate what your total change in income will be. And then we'll go through it, I don't know, like 1.5 minutes. Okay. So here we have our rate of change, which is 1.85 to the t. Since this is a t, we have dt. And then the bounds, we have to be careful. Here we're told that time is in months, and we're asked to find the income during the first year. So since time is in months, we have to represent our bounds in months. We have to follow the units that are given for your independent variable. So we have to integrate this from 0 to 12. So that was a little tricky. Hopefully you caught that. So then here, when we plug this into the calculator, we get $2,610.86. We know that this is about income. The income was changing in dollars per month, and we're asked to find the change in income, which is the original function. So that will be in dollars. So again, this is meant to highlight that there is a lot of examples where our function is a positive function, and we do want to get a positive outcome, right? However, we have not yet talked about what it means to have negative outcomes. So that's the piece that we need to add in here. So we're going to start with just a calculator example, where we're going to use a calculator to compute the area under the curve of x squared minus 1 from -1 to 1. Okay, so I want you to take 1 minute, plug this into your calculator just like we were doing before and see what you get out. Okay, so take a minute to plug that in and then we'll talk about it. Okay, so when we plug this into our calculator, we're going to get negative 1.333333 repeating. Okay, so now we have an instance where we are getting a negative value out. And you may think, hey, we can't have negative area. That doesn't make sense, right? How can an area be negative? Well, I want to remind you how we are calculating and defining area in calculus, right? So when we have integrals or when we do left and right hand approximations, what we are doing is we are looking up at the area between the function and the x-axis. So this is the function x squared minus 1. And so between negative 1 and 1, we have area that is below the x-axis, okay? So if we were to think about the rectangles that are calculating what's happening here, they still have a width of delta x, right? That's not going to change. Whatever the width we define it to be will be that. However, now our y values, which is what we're using to get the height, are negative. Right? So if you get a height of negative 0.5 and you multiply that by delta x, you get something negative. So what does that mean? That means that negative area represents something specific in calculus that's different than what we would be doing in, say, a geometry class. So what we do here is we assign meaning to the negative. So when we have area below the x-axis, we get negative values for our rectangles. And what that means is that the original function is decreasing, right? And so we know that's true because we know that if a function, a derivative function is negative, that means the original is decreasing. But this is telling us by how much it's going to decrease. So when we get something like negative 1.333 repeating, that means that the original function is decreasing by this amount. So we have to be really, really careful about this word area. So if I were to ask you for the area bounded by this function and the x-axis, but there were no integrals involved, then we'd still be talking about a positive area, right? We talk about a point in space. But when you talk about the integral, right, which is the area bounded by the curve and the x-axis, now we're talking about area computed with rectangles, and now we have negative area, okay? So the only time area can be negative is when it's in the context of computing this area under a curve with integration, okay? So you have to be really careful about that of when it's positive and when it's negative, and the negative piece only comes up in this context of calculus. So similar to the positive ones, you know, if we have a continuous negative function, then each term is going to have a y value that's negative, and therefore the area will be counted as negative. And so area on its own outside of the context of this is positive by definition. So we just really have to be careful that we're reading the problem carefully that we're doing to see if it makes sense for negative area to exist. Okay. Now, just an example of why we might want negative area, right? You can probably imagine a lot of scenarios, but here's just one example that we'll do. The average daily temperature from October 1st until January 1st is declining at a rate of F of T equals negative 0.9 T degrees Fahrenheit per day. There are roughly 92 days between October 1st and January 1st. Determine the change in temperature over this time period. Okay, so I want you to take 2 minutes, set up an integral, see if you can figure out the change here. We're expecting it to be negative because from October to January, we know that the temperature drops. So it'll make sense for us to have a negative answer here, but see if you can set this up. Make sure you put the right numbers in the right place, use the right variables, and then plug it into your calculator. And then in 2 minutes, we'll go through it together. Okay, take about 30 more seconds. Okay. So here we're looking at what happens over a 92-day period, because that's the approximate number of days. So we have 0 to 92. Our rate is negative 0.9 to the t dt. That's how we would set up the integral that we are representing. And when we plug this in, we get negative 9.49. And we know we're talking about temperature and the change in temperature, so degrees. So this is a scenario where having a negative answer makes sense, because what this tells us is that the temperature is going to drop by 9.49 degrees, right? It's going to go down. It's going to decrease from October 1st to January 1st. So there's just as many models that require us to be able to talk about a decrease in the original function as an increase. It really just depends on what you're modeling. And again, why does negative area make sense? Because negative area tells us that the original function is decreasing, right? That negative says it's going down, it's decreasing, right? And we need a way to talk about that. So that's why negative area makes sense. And that's what it means now when we see it. So one of the things we want to be able to do is we want to be able to look at a graph like this, and you can see that there's 4 areas labeled. There's A sub 1, A sub 2, A sub 3, and A sub 4. So for each of these areas, I want you to determine whether or not the area will be positive or negative, and what that tells us about the original function, right? So does that mean the original function is increasing or decreasing? So I want you to take about a minute and a half, think about what we see here visually, what the areas are going to tell us, and then how we can use that to talk about the original function. So just jot down a couple notes about what you think that means, and then we'll go through it together. Okay, take 30 more seconds. Okay, so let's start with A1. So what we see here is that A1 is below the x-axis. So that means when we calculate the area, okay, the area under the curve, that means we're going to have area that is negative, and the original function is decreasing. Okay, so when the area is negative, you are going to be decreasing. And again, we're talking about what would happen if we were looking at this through the lens of the definite integral. That's also going to happen for A3, right? So this was A1. A3 is also negative because we are below the x-axis. So the area will be negative, and that tells us that the original function is decreasing. Now for A2 and A4, the area is positive, and the original function is increasing. Now, the only reason we can make these statements in this case, we don't see an integral, but it says if we calculated it with the definite integral. So even though it's not written as an integral, it says that we're thinking about it in terms of the definite integral, which is why we can come to these conclusions. If this just said, look at the area and determine what the area is, they would all be positive. Like if we weren't considering it with the definite integral, then it would just be normal area and not the same context. So again, we're really trying to emphasize that you have to be looking at this through the lens of a definite integral to have negative area. So where we're going from here, we've talked about positive area, we've talked about negative area. In the next class, what we're going to do is we're going to say, what if you have a function where some areas are positive and some are negative? Like here, like how do we calculate the total change if your function's increasing and decreasing? We're also going to tackle the problem of what if you have two functions and you want to find the area between two functions instead of using the x-axis. How do we think about that? So that's where we're headed from here. I'm going to stop here for today just because I think this is a good place to stop. The next parts are a little more dense, so we'll spread that out. Try out the homework for 5.2, and then we will pick up the rest of the 5.3 section next class. So enjoy the rest of your day, get some sunshine, and I hope to see you soon.